All right, we will
But
go ahead and
talk
get
about that.
started. Welcome everyone here and online. Just for everyone in a room with other people, if you could just scan that QR code, they're counting so we can know our attendance. Glad to have you here for the third in our series of Cosmic AI seminars this semester. Today we will hear from John Carpenter, the ALMA Observatory Scientist, as well as Dustin Smith, who is CEO of a company in Charlottesville. We'll start off with John. John, as I mentioned, is the ALMA Observatory Scientist. He got his PhD from UMass Amherst, went on to a JCMT Fellowship in Hawaii, worked as a postdoc at Ovro before it was CARMA, and eventually became, I think, the Ovro director for a period of time. And since 2015, he has been the observatory scientist at ALMA and looked at their headquarters for ALMA in Chile. And he is also a pioneer in bringing machine learning techniques into observatory operations. We have a lot of projects going on, but he's going to tell us about one that he led a year or two ago to use machine learning in our ALMA peer reviewer assignment process. For those of us who work at observatories, that's very exciting. So I'm excited to hear about this. So I'll turn it over to John. Take it away.
Okay, thanks, Brian. Yes. Okay, yes. So I'm going to talk about one aspect of what we've been using to use machine learning for the ALMA proposal review process to assign proposals to reviewers. I'm going to provide a little bit of motivation about why we did this approach. Sketch the methodology, and then talk about some of the results, some of the metrics we have used to evaluate the performance of this approach. All right, so people in the NRA room, obviously I don't need to introduce ALMA, but for those who may be attending but are not astronomers, ALMA is the largest radio telescope in the world. It's located in northern Chile at 5,000 meters above sea level, and it's an international partnership between North America, East Asia, Europe, and Chile. It's an extremely powerful telescope, and it's in very high demand, and it's open to astronomers worldwide. Every year, we issue a call for proposals where astronomers can submit their proposals, submit their ideas, and how they want to use ALMA for their scientific research. We get roughly right now about 1,700 proposals per year, and they come from 44 different countries around the world. So it really is a globally recognized telescope that people want to use. And then it's heavily oversubscribed. So out of these 1,700 proposals, only about 1 in 7 will get high priority on the telescope. And so we have to review them scientifically to determine which ones are the best and which ones will be scheduled. And we use peer review. So astronomers themselves will evaluate their proposals, evaluate their strengths and weaknesses, and determine based on that what is the prioritized list of proposals that should be considered for the telescope. So we've been issuing call for proposals since 2011. And this graph here shows the number of proposals as a function of time. So when we started in cycle 0 in 2011, we had 900 proposals that were submitted, which at the time that alone felt like a lot, but it kept on growing. And by time about 2018 in cycle 6, we had doubled the number of proposals and we had 1,800 submitted. And it's been roughly around 1,700 or so ever since then. Initially, when we started ALMA, we had topical panels. So we would invite expert astronomers to come together to review their proposals. We might have 6 astronomers per panel in a variety of topics, and they would be assigned a group of proposals to review and prioritize. The problem is, as the number of proposals increased, we had to get more and more reviewers and more panels to review all the proposals. So by time of cycle 7 in 2019, we had 150 reviewers distributed over 25 panels, and they're reviewing anywhere between 70 to 150 proposals. And so it just became more and more of a logistical burden and a heavy overhead on the observatory to run that process. And after the pandemic in 2021, and almost late, we actually changed the observing mode, the peer review process, which has been called distributed peer review. And so each PI that submits a proposal, they have to designate one person to participate in the review process and review 10 proposals. So instead of having a few astronomers or 150 astronomers review 70 or 100 proposals each, we'll have about 1,100 reviewers, each reviewing somewhere between 10 to 30 proposals, depending on how many proposals they submitted. And so it's just a change in the model. And so instead of having face-to-face meetings, all of this is done basically remotely. There's no face-to-face discussions. Astronomers just review the proposals and submit their evaluations. But when you have 11, over 1,000 reviewers and you assign 10 proposals each, you have to have very efficient algorithms in order to assign those proposals to make sure you have a balance. They get proposals in which they're experts and which they can provide good reviews. So the process that we adopted initially in cycles 8 and 9 was basically based on keywords. And so when a PI or principal investigator submits a proposal, they select 1 to 2 keywords that describe their proposal. And this is from a list of keywords that ALMA provides. The reviewers would do the same thing. They would select which keywords they're experts in, and our algorithm would match proposals to reviewers based on the keywords. So that's what we used in cycles 8 and 9. And overall, it worked pretty well, I would say. 95% of the signed proposals matched the keywords provided by the reviewers, and 90% of the reviewers indicated they were experts or had at least some knowledge on the proposal topic. So that worked well, but there were some limitations. The keywords, they're broad and they can be imprecise or ambiguous, or at least they can be misinterpreted. Also, not all reviewers provided their keyword expertise. And so you sort of had to guess on what they were experts in. And for reasons which I still don't understand, some reviewers would select keywords and they were not experts. And so we would cite the keyword they selected, and they would complain and say, like, why did you get a proposal for this keyword? It's like, because, and so it's very confusing. But I would say the biggest operational challenge was that this algorithm that we had, I had tried to assign based on the keywords, it wasn't perfect. And there's some very obviously bad assignments where, let's say, an extragalactic reviewer would be assigned a proposal in circumstellar disk just based on there's too many constraints within the process. And so we would spend 3 days trying to manually, to redo these bad assignments because we knew the reviewers would not accept such egregious assignment. And so this was a heavy burden on the observatory in terms of redoing these assignments. So based on this, we decided to try in cycle 10, we adopted a new approach using machine learning and optimization algorithms. I'll describe the process on the next few slides, but basically, sorry, is there a question?
Okay. But that's all that is.
Oh, so stuff like the fire.
Yeah.
No, I think you can go ahead. Yeah, it was somebody.
Okay. And so we would use machine learning. So instead of relying on keywords, we would use machine learning to infer the topic of the proposal. And based on the proposals the reviewer themselves has submitted, we would infer the expertise of the reviewer. And then you can compute the similarity between the reviewer expertise and the proposal topic and use that as a measure of how well a proposal aligns with the reviewer. And then there's some new optimization algorithms that we adopted from computer science that can take these similarities and produce an optimized assignment algorithm. And this was all done using Python, Jupyter Notebooks, and Dataiku, and the Jerobi optimization platform. Okay, so how do you turn the topics for each proposal? So we have the history of all the ALMA proposals that have been submitted to ALMA, and we basically use machine learning or topic modeling to infer the topic of the proposal. We use LDA for our process, but we actually find that this wasn't so critical. So other machine learning techniques, for example, for counting the frequency of words, that also worked very well. As I'll describe in the next slide, we just got slightly better results using the LDA technique. And what this does is basically determine, based on all the proposals that have been submitted, it reduces that down into n particular topics where I select the number of topics that I wanted to break it down to. And a topic is just a cluster of words, which I'll illustrate. And then any document or any proposal is then just basically a distribution of these topics. So this is all done within the GenSim Python library. What the results I'm describing is based just using 50 topics to represent the proposals. But that's somewhat of an arbitrary. So what's a topic? This just shows an example with two topics. Let's say for topic 1 might be the words quasar plus host plus galaxy plus AGN plus any number of additional words. And each word is given a particular weight that I show here. And very broadly, you might consider the topic 1 to be, associated with quasars. And a topic 2, maybe words disk plus gas plus planet or chemical. And so very broadly, this topic represent circumstellar disks. And for any given proposal, then you can break it down into what is the strength of that topic within that proposal. Well, phi of n represents the strength of the words for a given topic, and theta of n represents what is the strength of the topics for a given proposal. And so you basically just reduce the proposal down into individual topics, and each one has a particular weight. So how does this work in practice? And so we tested this by computing the similarity between any two proposals. And the similarity is just basically given by the dot product between the two topic vectors, between any given two proposals and with appropriate normalization. And so what we did was for a given proposal, we identified what were the top 10 proposals that had the highest similarity. And so when you submit a proposal, you actually select not only the keywords, but the category you're submitting to. And you would expect that the nearest matching proposals should be in the same category if this algorithm was working well. And what this matrix shows is that for a given submitted category, what fraction of the nearest closest matching proposals are in the same category. So in category 4, which is circumstellar disks in the solar system, 80% of the proposals, of the closest matching proposals, were also in category 4. 1% were in category 5, which is stars, 3% were in category 3, which is star formation, and 0% were actually in categories 1 and 2. And so this is actually working pretty well. These outliers here in the different categories, they're not necessarily bad matches, because sometimes people would submit the circumstellar disk categories, circumstellar disk proposals into category 3, or there's some proposals in category 5, which are also looking at disks, but perhaps around evolved stars. And so it doesn't necessarily, it's a bad match, but I think it really reflects more of the ambiguity between different science categories. You really see this in categories 1 and 2 with our both galaxies, where there's about a 20%, 18% overlap, where the closest matching proposals are in the other category. But nonetheless, there are some outliers, especially if you get some rare words, like it's for proposals looking at, for example, looking at magnetic fields using polarization, it might match a extragalactic proposal with a proposal looking, around, circumstellar disks based on magnetic field. And so there are some outliers or false matches, I would say, based on this algorithm. But overall, we're reproducing well the fraction of proposals, the nearest proposals that were in the same category. And it's actually based on this plot, which we decided on using the LDA technique over the other approaches that we matched, which gave slightly better positive, slightly higher values across the diagonal in this matrix. Okay, so that's how you determine the topic of the proposal, and gave us some confidence that we were measuring the topics fairly well. And basically just do the same things for the reviewer. You just look at their proposal history, measure the topics in their proposals, and basically come up with a reviewer matrix for their submitted proposals. Now, we could use their published papers instead of their submitted proposals. The issue there is that we can't always unambiguously say the issue. We cannot there's ambiguity in identifying the reviewer in the published papers, while in the ALMA ALMA system, they have each reviewer has to be registered, and so we know exactly what their um, 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 user ID is. We know exactly which proposals they were located on, so we can so it's unambiguous, and so that's why we use the ALMA proposals. Okay, so we have the reviewer expertise, we have the proposal topics, and then we can just use the dot product to compute the similarity between any proposal and any reviewer, and you get a matrix that describes all the similarities between the reviewers and the proposals, and this is our basic input into our optimization algorithm. So the question is like, the assumption behind this is that if you have a higher similarity, you have more expertise on that proposal, but is that actually true in practice? And we tested this by using a reviewer survey in the previous cycles. And so in cycles 8 and 9, we asked the reviewers based on our old assignment algorithm, were they experts in the proposal or not? And so they said they were experts, they had some knowledge or little knowledge. And after the fact, we can go back and compute the similarity between their assignments and the proposal topics, their assignments and the reviewer expertise that we infer, and can compare the similarities. And so that's what's shown here for cycle 8 and cycle 9. And so the blue curve shows the cumulative distribution of the similarities. Similarities go from 0 to 1, where 1 means the maximum alignment between a proposal and a topic. And so the yellow showed where the reviewers said they had some knowledge, and the light blue said they had little or no knowledge. And as you can see, is that when they said they were experts, they generally have higher similarities than when they had some knowledge or little knowledge. So this gives us some confidence then is that the similarities are measuring some level of expertise among the reviewers for a given proposal. So after that, before we actually do the assignments, we do have to do a little bookkeeping, is that we want to flag conflicted proposals. So obviously, a reviewer should not be reviewing their own proposals. And we also wanted to flag, just as to make it process more robust, we wanted to flag bad matches. For example, a cosmology proposal should not be reviewing proposal on, on Jupiter, for example. And so we would actually, based on the keywords that were provided by the PI, we would actually go through and flag assignments that we know in advance that we don't want, period. From that, we produce our final similarity matrix. And then the next step is just optimize those assignments. And this itself is actually, a subject of research. It's like, how do you optimize the proposal assignments? Because each proposal has to be reviewed 10 times in our system, and each reviewer has to be assigned 10 proposals. And so that provides some constraints on the system. One approach is that you just want to maximize the global similarity across all assignments. So you want to maximize the total expertise over all proposals. That's an approach that's been taken in some venues. And here's just a toy example of how that would work. And so this is an example of this with 3 reviewers and 3 proposals. And this just shows a similarity matrix in this toy example. And if you want to maximize the similarity, proposal A, we assign to reviewer 1 because it has a similarity of 1. Proposal 2 is assigned to reviewer 2, which is similarity of 1. But proposal C, because that's the one that's remaining, is assigned to reviewer 3, but has a similarity of 0. And so you actually maximize the similarity, but you can argue that proposal C is at its disadvantage because it doesn't receive an expert evaluation. So there's another approach that one could take, is the approach that ALMA has taken, is that instead of maximizing the sum similarity, you maximize the minimum similarity. So you want all proposals to have a certain level of similarity between the reviewer and the proposal topic. And so it basically more precisely what you basically want to take the proposal, which has the least available experts, assign the proposal to it first, and then take the second most proposal, which has the least experts, and assign that. And do the proposals which have the most experts available, do that last in order to even out the expertise distribution. And this is an algorithm that's been used in computer science called peer review for all. And this is something, so we've been in collaboration with the person who wrote that algorithm, and we've adapted it for our purposes. And so for going back to this toy example, so since proposal C has the least overall expertise, we actually assign it first. And so this would be assigned to reviewer 1. And then proposal A, among proposal A and B, proposal A, of the 2 reviewers that are remaining, this would have the least available expertise, so it's assigned next, and it's assigned to reviewer 2. And then proposal B is assigned to reviewer 3. And so the total sum of the similarities is less than before, but it's more balanced. So all proposals reviewed by someone, by a reviewer, has some level of expertise. So that's the basic approach behind the algorithm. And this shows in practice of how it looked like. And so this is showing the histogram of the similarities between this proposal assignments based on the old algorithm. So this is from cycle 9, where we use keywords. And then in orange shows in cycle 10, when we use the machine learning optimization algorithm for the first time. And you can see is that the similarities overall are skewed to much higher similarities for the new assignment algorithm than the old assignment algorithm. And the average similarity increased by 51 percentage points. And so overall, based on this, you would expect there's better alignment between the proposals and assignments to the reviewers. This shows the reviewer feedback, which is perhaps the most important thing to consider. And so this is based on the reviewer survey. So we've continued this reviewer survey each year. And this is showing the histogram showing what fraction of the assignments the reviewers rated them. They're in their field, had some knowledge or little knowledge. The 2 grays when we have the keywords, and the oranges is when we have the new algorithm. And so you can see is that when we adopted a new algorithm, the number of the percentage of reviewers who said they had the proposal was in their field increased by nearly 50%. And perhaps more importantly, the fraction of assignments where reviewers said they had little or no knowledge was basically cut in half. It's only down to 5 or 6%. So overall, there seems to be better alignment between the proposal assignments and the reviewers. So summary in the next step. So as I said, I think this algorithm demonstrated that we get better alignment between the proposal topics and the reviewer expertise. We have a few metrics that demonstrate this, including feedback from the themselves. I do think there's ways that the machine learning implementation can be improved. Right now, we rely on the keywords and categories to filter some mismatches. I think perhaps there's there's the algorithms are always improving, and I think within our existing framework, I think we could perhaps use more topics to get better refinement. But I actually think the more provocative question is alignment too good? Should reviewers be exposed to more different range of topics than we currently have? And I think that's something that within the proposal handling team here at the ALMA Observatory is something that we've been discussing. And we actually took steps last cycle to basically flatten out the distribution. And so try to give people a little bit more range of topics. But I think that's something that we continue to examine. And I think there's other applications that we can use within the proposal review process for this. Can we use AI and machine learning, for example, to identify and monitor the quality of the reviewer comments? So that's something we're also looking into. And I think longer term and perhaps more provocative is can AI be used to perform the evaluation process itself? Based on my experience so far, I would say currently no. But these technology is rapidly evolving and it's improving, by leaps and bounds from year to year. And so this may not be, in the future, this may be more viable. And my last comment is that this work is published. So we had an article describing the algorithm that was published this year. So Andrea Corvillon is the lead of the proposal handling team at the JAO, and Nihar Shah, he's our colleague from computer science, and he introduced us to a lot of these techniques. So here's the QR code for that paper. So I'll be happy to answer any questions.
Thanks, John. We have time for questions. We'll start in the room here. Yeah.
Okay. Hi. So it seemed like in the last slide that the fraction of proposals for which reviews had no expertise was increasing over the last 3 cycles, and my field was decreasing. Do you know why is that the case?
I have the suspicion because in cycle, like I said, I was worried about the, is alignment too good? And so in cycle 11, what we did was actually put limitations to how much overlap there can be between different proposal sets that were assigned to reviewer. So that would require not necessarily, so we weren't necessarily requiring the absolute best alignment just based on the similarities. And in cycle 12, we actually flattened out the distribution where we capped the similarities at 0.5. And so similarities between 0.5 and 1 were all considered to be equal. So you had equal chance of getting similarities in that range. And so this was just all trying to just broaden the distribution of topics that any individual reviewer gets, although they're still relatively experts. And so I suspect it's that's part of the reasons, but this is still factor 2 better than we were doing before. And so I think tolerating this 1% range, I'm sort of okay with that. I would not want to get up to, I'm trying to do much better than we did before, is basically what I'm trying to aim for.
Thanks.
Another question?
Exciting work. So I was wondering, initially, you mentioned that the reviewer expertise is determined based on the reviewer's past submitted proposals. I was wondering, what would you do in the case of early career reviewers who would not have an extensive history of past submitted proposals? Is it possible to also incorporate, say, a publication history and use that to determine the expertise?
Well, way the system works, every reviewer, since they have to be part of an ALMA proposal, because you have to be a PI or co-I, so there's guaranteed that somewhere there's they're part of an ALMA proposal. And so even an early career researcher, if a student, they're submitting a proposal, the reviewer, they submitted that proposal. And so we use the proposals in the current cycle as well as the previous cycles. And so every reviewer is guaranteed to be a co-I, at least a co-I or PI on some ALMA proposal at some point. Now, what does happen is that sometimes the reviewer will say they're experts in the category in which they have not submitted a proposal. And so we have various steps that we evaluate. And it could be that, we can evaluate their expertise because they say they're an expert in stars, but they're a co-I on a proposal in galaxies. And so at that point, we just say, okay, we're just going to assign you proposals in category 5 on stars. That's the best we can do because we don't have their expertise. But every reviewer is an expert, has to be a co-I or PI in some proposal, even if it's a first-time student.
We have one question online, and then we should probably move on. From Evan Smith, who asks, "Are you doing human spot checks on the matchups? For example, having a human grab every 20th proposal and check that the expertise matches the proposed the assignments."
Yeah, we have various metric algorithms that we run. So we don't do it as systematically as that, but we look at various metrics of looking at which proposals in different categories are assigned, and we'll do a spot check of those. We have various other constraints that we put in, making sure that students, there are assigned proposals in the same category that they cleared their expertise. And so we have checks on that. So we have various things that we do look at. But obviously, when you have 1,700 proposals, it's only a small fraction that we can look at. But we still have, even after the proposal assignments are done, the reviewers, they can declare conflicts on their proposals. And normally, if they say they're not an expert on the proposal itself, we don't accept that. But it was clearly the case where the algorithm failed, then we would you would actually reassign things. But it's only been actually in a couple cases where we actually accepted those type of things. So I think for the most part, we're not getting to the assignments aren't totally mismatched.
Okay, well, let's thank John again.